Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics in introduction. We've seen that heteroskedasticity affects inference. Now the question is, how do we detect it? And the simplest way is to look at the residuals. Keep in mind, we're looking for common patterns like a fan shape, which means increasing variance, an inverted fan, clusters with different spreads. So basically we're looking for a non-constant spread. The two most common tests or formal tests that are usually used to detect heteroskedasticity are the Bruce-Pagan and the White test. Before we jump into R to see how exactly to run these tests and interpret the results of the test to make a decision on whether we have heteroskedasticity or homoskedasticity, let's just very quickly go through the process of what happens behind the scene with the Bruce-Pagan and the White test. So the Bruce-Pagan test starts from a regression where we have y equals to beta 0, beta 1x, beta 2x plus a error term. When we estimate this model and we get the residual u hat, we build u hat square and we run a regression of the residual square on the initial x variables, so on x1 and x2. From then on, the Bruce-Pagan's test null hypothesis is that these delta 1 and these delta 2 are actually equal to 0. And the alternative is that at least one is not 0. Keep in mind, your null hypothesis is equivalent to saying that you have homoskedasticity, while your alternative is indicating that you have heteroskedasticity. Okay. Now, in order to run such a test, the easiest way would be to do an F-test. Okay? Because as you can see, we're looking jointly what is happening to these delta 1 and delta 2. Okay? But there are actually two ways to test these restrictions. The F-test you already know, but there's a second approach, which is called the Lagrange multiplier test, or the LM test, which instead of comparing models, asks the question, how much does the auxiliary regression explain? Okay? Because as you can see here, we are making use of this auxiliary regression where we're using the residual square, okay? And if the regressors explain a lot of the variations in this residual square in here, it means we've got evidence of heteroskedasticity. Now, us saying that the regressors explain a lot of the variation in the U hat means that the R squared of this auxiliary regression would have been quite high. And because we're involving now the R squared, it's no surprise that actually the LM test, in order for us to compute it, uses the R squared, which we're going to see in a moment. The second most common test is the White test. For simplicity, I'm just writing H0, so the null hypothesis as homoskedasticity and heteroskedasticity as the alternative, but keep in mind we're doing exactly the same assumption, or like we're using the same intuition as the Bruce-Pagan test. For the White test, however, what changes is the auxiliary regression that we're using. Think of the Bruce-Pagan as like a more specific case of the White test, because what the White test uses is not only the x1 and x2 variable that we had already included in the Y test. So far this we've already seen in the Y test. Now we are including also x1 square, x2 square, and the cross product of your x variables. Okay, so the Y test is a bit more general. And again, when we say we're testing for a homoskedasticity, we're checking that all of these coefficients are jointly equal to 0. Again, you can do this through an F-test or you can do this through the LM test. The way to compute the LM test is by using the number of observations and the R square, again, of the auxiliary regression. And this is distributed with a chi-square distribution of p-1 degrees of freedom. A quick overview before we jump into the application in R is what's the difference and when should we use F-test or R-test or the LM test? The answer is, well, you can use whichever information is the most available to you. Because the difference between the F-test and the LM test is that for the LM test, you are basically using mainly the auxiliary regression and more specifically R-square. And the F-test, you're actually using both models, so you're in order to get to that result. The test statistic for the F-test, obviously an F, while for the LM test, you have N times R-square. You've got the distribution for the F-test is going to be an F distribution with Q degrees of freedom as the first one, and then N minus K minus 1. Then ultimately for the LM test is chi-square distribution with P minus 1. And keep in mind, they both are testing exactly the same null hypothesis, is exactly the same test, is just the way that you are getting to the answer is through a different method. Okay? So without further ado, let's go and see the application of this test directly into R. For this case, we're going to use a data set from the Wooldridge and its birth weight. The model that we're going to test is whether birth weight depends on the number of cigarettes and the family income that the woman giving birth has. Since this is going to use an already available Wooldridge data set, you need to obviously either install the packages in case you have never done that before, and then also the library. The LM test library is what allows for us to run the Bruch-Pagan test. And then because we're gonna want to use robust standard errors, which you'll have another video explained why do we have to use and what does the standard error do for us. We're using the sandwich library and then for plotting ggplot2. I am going to install them again simply because I recently updated my R. And then I'm going to quickly upload the data and show you very quickly the head of the data set. So as you can see, we've got the birth weight in here, which is in ounces, and then we've got cigarettes, number of cigarettes. For the first few observations, we can see that actually the number of cigarettes, it's actually 0. I'm sure if we go further down, we're going to see different numbers as well. We can have a summary and we can also double check that directly based on that. So as you can see, the number of cigarettes goes from a minimum of 0 to a maximum of 50, but we can see here that the mean is actually on average like 2.08, so approximately 2 cigarettes. Again, we need to have mothers who smoke and don't smoke so that we can really check whether smoking does affect the birth weight. And we can see that very clearly with this tabulation. So you can see false. So we have cigarettes being equal to 0 as false in 212 observations and as true in 1,176 observations. The model, again, is very straightforward, and we can run a regression and see the results. For now, we can directly see that both cigarettes and family income are actually highly statistically significant. But as you remember, we said that the moment that we have heteroskedasticity, while we can have estimates that are unbiased, we can't be sure about the certainty or uncertainty of these coefficients. So let's now have a look at what is going behind the scenes and whether we have maybe results that are affected by heteroskedasticity. So of course, we would need the residuals of the model. And at the same time, we're going to take the fitted values of the model just for the graph purposes in here. So once we save this information, we can draw the graph, which will show us how are the residuals behaving based on the fitted values. Now, if we had heteroskedasticity, we would have expected that cone shape, like or fan shape. We see that in this graph in here, however, we don't really see that we just see that here for smaller like smaller fitted values, we've got fewer observations at most, but they are quite well spread around the zero. So on average, you could even think like, well, it looks like it's on average a zero. And even in the places here where we've got more cluster, like more observations, it does look like you've got sort of the same kind of amount of dots both below and above the zero line in here. So that's an indication that maybe this model is not really suffering from heteroskedasticity. Of course, you should never just base your answer on the graphical interpretation. We can also see for the fan shape or the changing spread for particular key variables, like for instance, we could just use cigarettes. In the graph for cigarettes, again, we see that that the spread is not really changing a lot as the number of cigarettes is changing per day, okay? And they are quite centered around the zero in here. We can look at the other variable as well, which is family income, to see, well, what about if heteroscedasticity is coming because of the other X variable, family income? And we do see similar pattern in here as well. So it's quite centered around zero. So from graphs alone, for now, our assumption is very likely that, well, it does seem like we have homoskedasticity in here instead of heteroskedasticity. But let's make sure that that is indeed the case. So running the Bruce-Pagan test, we would need to run BP test and save the results into a variable, which is then displayed for us. Keep in mind, what is going to happen actually, for instance, in R, is that you're not going to really get the F test or whatever statistic that you would have wanted to get. Of course, if you give more specific code to R, you can get that information as well. But the easiest and also, in a sense, the most precise one would be to look simply at the p-value in here. Okay, this is a Bruce-Pagan like statistic, that as they call it in here. But if you look directly at the p-values, you can see that this is quite a high p-value. So you would expect to not be able to reject the null hypothesis of homoskedasticity. And in this case, the test result coincides with the story that we were looking into the actual videos. Okay. We can do the white test. Now, for the white test, the code is slightly different, but look that we are still using the BP test command in here, because if you remember, I already told you at the beginning of this video that the white test is just a more general way or a more general form of the Bruce-Pagan test, or the Bruce-Pagan test being like a more specific version of the white test. So remember, for the white test, we were using also the squared versions of the X variables as well as the cross product of that. So if we run the Y test, normally we would expect to see exactly the same answer, basically homoskedasticity, and the p-value also for the Y test in here is quite high, which means we fail to reject the null hypothesis and we have homoskedasticity, so we don't have to worry about heteroskedasticity. The last bit, which you'll see even more explained on why does this happen in the moment that we fix with robust standard errors, is that when you apply standard errors, technically you are not changing the estimation, you're just changing the structure of the variance covariance matrix. So if we run exactly the same model, but with robust standard errors, especially in this case where we have homoskedasticity, you shouldn't see a huge difference in your result. So in here, this is what we had in the model that we ran earlier, okay? And if we do exactly the same but with robust standard errors, keep in mind, we don't need to run the regression all over again. We're just adding the robust standard errors, okay? If we run this and we see the actual numbers, we can see that, again, estimates, they don't change. We were not expecting them to change, but even the standard errors in here have not greatly changed because we had homoskedasticity. So even if you apply this robust standard errors, not much is basically going to change. I hope this example was helpful, at least so you could see a little bit like what is happening and what should we be looking at in graphs, especially when we try to detect heteroskedasticity. And stay tuned. I'll see you in the next videos.